So for question A, we've been told that a scientist is studying the growth of two different populations of bacteria. The number of bacteria N in the first population is modeled by the equation N is equal to A times E to the power of K times T, where T is a positive value since T is time. A and K are also positive constants. And it is given that initially there were 1,000 bacteria in the population at the start of the study, and that it took exactly 5 hours from the start of the study for this population to double. Now, in part A, we've been asked to find a complete equation for this model. So essentially, we know from the 2 points that we need to find the actual equation for the model. So we know that if our general equation is N is equal to A e to the power kt, then our initial population is 1,000, so that means that A is 1,000. So N is equal to 1,000 e to the power kt. Now, we now have to find the value of K, and for that we use the second bullet point of information, where that after 5 hours, the population of the bacteria doubled. So we now know that if the starting population was 1,000, the new population at 5 hours would be 2,000. So we know that 2,000 is equal to 1,000 times e to the power kt, and we can go ahead and divide both sides by 1,000 to yield 2 is equal to e to the power kt, and then use our logarithms to solve the value for K. So if I go ahead and input a logarithm to both sides of this equation, I get the natural log of 2 is equal to the natural log of e to the power kt. And as we know, the natural log of e is just equal to the power. So that means that ln2 is equal to kt. And we can go ahead and find K as equal to, so K would be equal to ln2 divided by T, where T is equal to 5. So ln2 divided by 5 is equal to 0.139. So this is our value of K. And this means that we can find the actual equation to be N is equal to 1,000 e to the power 0.139 times T, and that is part A. Now, in part B of this question, we've been asked to find the rate of increase in the number of bacteria in this population exactly 8 hours from the start of this study. Now, the rate of increase denotes the derivative of this equation. So essentially what we have to do is find the value of the derivative of this equation at 8 hours. So firstly, let's go ahead and do that. So the rate of change in the population would be dn by dt, and all we have to do here is differentiate this equation. So that would be 1,000 times and the derivative of e to the power of a of a function is just the function as a coefficient of e, so 0.139 times e to the power of 0.139t. So this is it's a very simple differentiation whenever you're dealing with e, because it essentially stays the same. All you have to do is bring the coefficient of whatever is in the power to the front. So now we have this, we can go ahead and find out the value of this rate of change at time of 8 hours. So all we have to do now is substitute t is equal to 8 into this equation. So that's 1,000 times 0.139 e to the power 0.139 times 8. And if you pop this into your calculator, you should get the value of 422.6. Now, the question has asked us to give our answer to two significant figures, so we can go ahead and round this down to 420 to two significant figures. And that is part B. So for part C, we have been told that the number of bacteria M in the second population is modeled by the equation of M is equal to 500 e to the power of 1.4 times K times T, where K is the exact same value that we found in part A, and T is the time and hours from the start of the study. Now, it's also been told to us that after a given amount of time, capital T, the number of bacteria in both populations is exactly the same. And using this information, we have been asked to find the value of T. So if we go ahead and just write down the two equations that we know. So for the first population, we know that the number of bacteria is equal to 1,000 times e to the power 0.139 T. And for the second population, this number of bacteria is equal to 500 times e to the power of 1.4 times 0.1 0.139t. And we know that if the number of bacteria is exactly the same, so we need to equate these two equations together in order to find the time at which the number of bacteria is the same. So let's go ahead and do that. So if I go ahead and equate 1000 e to the power 0.139t is equal to 500 e to the power 1.4 times 0.139t. And if we go ahead and realize that this power here of e on the right hand side is simply equal to 500 times e to the power of 0.139t to the power of 1.4. This becomes very easy to simplify. So if we go ahead and divide both sides by the right hand side term, we get 1000 e to the power 0.139t divided by 500 times e to the power of 0.139t to the power of 1.4. Now we can go ahead and equate this to 1, because of course if we divide it from the right hand side entirely, this is left as equal to 1, and we can cancel out this fraction here. So, well, we know that 1500 cancel out to make 2, so we can do that. So that cancels out to make 2, and then this e term can be cancelled out by simply cancelling the whole thing out on the numerator and then taking away 1 from the power in the denominator. So this then simplifies down to 2 divided by e to the power of 0.139t to the power of 0.4, and then we can equate this to 1, and then using this equation we can solve for t. So essentially, if I again bring this in entirety to the right hand side, so this would be 2 is equal to e to the power of 0.139t times 0.4, and then we can use our natural logarithms to help solve for t. So if I introduce the natural logarithm to both sides of this equation now, I get ln2 is equal to ln of e to the power of 0.139t times 0.4, and we know that the natural logarithm of e is just 1, so this further simplifies down to ln of 2 is equal to 0.139t times 0.4, and then we can divide both sides by 0.139 times 0.4 to get t is equal to ln2 divided by 0.139 times 0.4, and this is equal to 12.47, which roughly rounds to 12.5.